Hello, Chem 30 students. So today we are looking at our second part of organic reactions. So in the last lesson, remember we looked at things like reforming and cracking, basically a lot of reactions that are used in the petrochemical industry. With those reactions, just keep in mind you don't really need to know a lot of specifics and details about them. You just kind of need to know the general idea of what they're doing and what they are used for. Today we're going to look at reactions where you actually need to be able to predict the products, write and interpret balanced equations, and you should be able to kind of define how the reaction works and identify and provide examples of these types of reactions. So the ones we're going to look at today are addition, substitution, elimination, and combustion. We looked at combustion last time. So just these three, and we'll look at esterification in part 3 of organic reactions. So we're going to start out looking at addition reactions. So with an addition reaction, basically what happens is you have like an alkene or an alkyne, something with a double bond, so an unsaturated hydrocarbon. And what happens is, if you remember, we talked a little bit in a previous lesson about how these double bonds are not particularly stable. And so essentially you have a smaller compound, like in this case hydrogen bromide, that's able to come in and destabilize that bond so that the two bond spots that are freed up on the carbon become occupied by the components of this smaller molecule. So in this case, that means the hydrogen bonds onto this second carbon here, so that instead of having 2 hydrogens, it now has 3. And the bromine then attaches onto the carbon that also has an open bond spot. Okay, so we end up with an alkyl halide, right? So yeah, basically that's all you really need to know there. Now, be aware that this could be a different type of molecule. So we can have halogens like we see here, hydrogen halides is what we have here. You could have a halogen, which would just be like Br2 if it was kind of the same as this. And in this case, you would have bromine take the place of both of those spots. So you would have like 1,2-dibromoethane, basically. The other thing you could have come in is water. And so in that case with water, you're going to see that we think of water as being broken down into hydrogen and hydroxide. And so then what you would have is a hydrogen on this one and a hydroxide on this one, which would make it into an alcohol, right? Because that would be our hydroxyl group. Okay. Only alkenes and alkynes undergo this kind. So as we go through these reactions, it's a good idea to kind of be familiar with what the reactants are and what the products are so you can easily identify them. There will be a summary chart at the end of this section that kind of goes through some of that. So yeah, that's the basics of an addition reaction. Now, with addition reactions, one kind of special version of this is an addition reaction that converts unsaturated hydrocarbons, so that's alkenes or alkynes, into saturated hydrocarbons by adding H2. So your hydrogenation is like adding hydrogen, right? Molecules do this to become more stable. So remember that a alkane is more stable than an alkene, so that can achieve this. The only thing you have to keep in mind is it does not work on benzene. So despite the fact that benzene has those double bonds, just keep in mind that it is very stable because of the unusual way the electron configuration works in it. So it's not affected in this way. There's a little bit of information here. Just you may have heard of hydrogenation before with relation to dietary fats. So hydrogenation is a process that can actually be used to convert unsaturated fats into saturated fats, which, maybe isn't the best because saturated fats have maybe not the best health benefits all the time, especially if they're consumed in excess. Partial hydrogenation can lead to the production of trans fats, which even more, we're more aware that this is even worse in terms of diet, right? Trans fats. Lots of countries are actually phasing them out. So let's go through some examples because with these types of reactions, you will have to understand the mechanism slightly of the reaction and be able to predict the products. So in this one, we have pent-2-ene reacting with water. So usually I find the best thing to do with these is to draw them out, especially when you're just getting started. So pent-2-ene means we're going to have 5 carbons in the chain. The second carbon is going to have a double bond, so if we call that carbon 2, we're going to have a double bond there. And then that means this is going to be like CH3. And then this carbon is going to have 1, 2, 3, so we're only going to have space for 1 hydrogen. Same thing over here. And then 2 and 3 on the end. Okay, so there's our pent-2-ene, and we're reacting it with water. So again, if you want to think about when you're drawing these out, think of water in terms of reactivity as the hydrogen with the hydroxide group. And so basically what's going to happen is this double bond is going to relax, allowing the hydrogen to come in and take the place of that double bond on one carbon, and the hydroxide to come in and take the place on the other carbon. So essentially what that means is, let me see, I wanted my highlighter. We're going to have this component jump in here, and we're going to see the disappearance of that double bond. So I'm just going to draw the product down here. We're going to have CH3 on the end, and then we're going to have carbon with a hydrogen, but one of these double bonds gets replaced by the hydrogen from the water. So this is new atom on the molecule. And then we still have the bond to the other carbon, which has the other hydrogen, but it is now going to accept the hydroxide. So there's our 2 components from the water. And then the rest of the molecule will just be as usual. So it's going to be CH2, CH3. I know that isn't like I kind of did like expanded or structural and then condensed over here, but I just didn't want to make things too messy. So here we can see how our products would be, and if we wanted to name that, we would call it, let's see, 1, 2, 3, 1, 2, 3. So it's pentan 3 all. Now, of course, there's 2 possibilities for this, right? In this case, we drew the hydroxide on the third carbon, but you could also just as easily have it reversed. So it could be or pentan 2 all. Okay, so 2 possibilities there. I'm not going to draw out the second version because it would basically be the same, but with the hydroxide on this carbon instead. All right. Let's try another one of these. Predict the products of the reaction by drawing the complete reaction. Okay, so we have C3H4. So we have 3 carbons, and we only have 4 hydrogens. So keep in mind some of your formulas that we use for considering whether we have an alkane, alkene, or alkyne. So with the alkene, it's going to be CnH2n. So all of them have this component, but remember for an alkane it's +2, for an alkene it's just 2n, and for an alkyne it's 2n minus 2. Okay, and so basically that would be 3 times 2 is 6. So we would have 6 here, and because we only have 4, we know it has to be an alkyne because it's -2. So with an alkyne, that means we have to have a triple bond, and with 3 carbons, there's only 2 possible places for that, but because we number from whichever carbon has the triple bond, it doesn't really matter which side because they would both be on the first carbon. Okay, so there's our triple bond. So this carbon has 3 bonds here, so it needs to have a hydrogen attached. This carbon has 3 bonds here, but it also has to link to this carbon, so it can't have any more. So the remaining 3 hydrogens will be found off of this guy. Then we're going to react it with iodine. So we're going to have basically 2 iodine atoms there coming in. And what's going to happen here? Well, we only have 2 iodines, so that means one can replace each end of one of these bonds. So we're going to go from a triple bond down to a double bond. So basically we're going to have this carbon with the hydrogen attached off of it. And now this is going to become a double bond. And we're going to put off of this carbon, we're going to have 1 iodine. So now this carbon has 1, 2, 3, 4 bonds. The other carbon is going to have also an iodine attached onto it because it also broke that third bond. And then this carbon's going to have 1, 2, 3, and then the 4th bond will go to this last carbon, which is CH3. Okay, so again, we see here is our smaller molecule that comes in. And we see how it's added into the molecule, breaking up that multiple bond. So in terms of naming, we would call this, we have an iodine on each of the, like carbon 1 and carbon 2. So that means it's going to be 1, 2 diiodo prop. And then this is a alkene, so we just need to remember to identify the location because otherwise it could have, like you could have had a multiple bond here and the iodine's there. Maybe not, but let's just identify. So the double bond is on the first one, so prop 1-ene. Okay. So the next reaction we have here, C3H4 plus 2I2. So you might be wondering, why are we doing the same reaction again? Well, keep in mind this isn't actually the same reaction because now we have more iodine available. So what's going to happen with that? So let's just keep in mind here our structure for C3H4. We had a triple bond and then a carbon and then CH3. Now we're adding in, we have 4 iodine atoms, right? 2 iodine molecules. So when we go to think about the products here, the first 2 are going to break this triple bond, and the second 2 are going to break down the double bond. So we're left with a single bond. So basically what we're going to have now is the hydrogen attached to the carbon. The first bond is replaced with an iodine, and the second bond that gets broken is replaced with an iodine. And then it's bonded to the other carbon, still with the single bond, and that carbon can also accept 2 iodines. Okay, so now we have all 4 iodine atoms accounted for, and then we're still just going to have this methyl group on the end there, CH3. So now, what do we have here? 1, 2 tetraiodo. Actually, you know what? It would be 1, 1, 2, 2. And I don't know where my whiteout is. Anyways, it'd be 1, 1, 1, 1, 2, 2 tetraiodo ethane. I guess I should just write that. Tetraiodo ethane. Okay, so totally different product from what we saw in the previous reaction there. Pent-2-ene reacting with hydrogen. So this is going to be an example of that hydrogenation, which is a special version of addition. So again, we have pent 1, 2, 3, 4, 5, and the double bond is on the second carbon. So this is going to be CH3, CH, 1, 2, 3, 4, and then again CH, CH2, CH3. Okay, and it's reacting with hydrogen. So remember, hydrogen is diatomic, so it's going to come as HH. And what's going to happen? Each hydrogen is going to replace one end of the double bond here. So we're going to end up adding a hydrogen here and adding a hydrogen there and removing our double bond. So we're going to end up with CH3 dash, now this is going to be CH2, the other one is going to be CH2, and then the ending stays the same, so CH2, CH3. So we end up with just plain pentane. So, summary of our addition reactions, some of the special names that we have for them. If you're adding just hydrogen, it's called dehydrogenation, and you end up with an alkane. If you have halogenation, you are adding like a halogen, and that is going to take the place here, so you're going to end up with an organic halide. If you have, same thing, so this one was alkene, right? And you're going to end up with an organic halide. If you have an alkyne and you put in a halogen, it's going to end up being an alkene, but an alkene halide. Hydrohalogenation is just when you're adding on a compound that has hydrogen and a halogen in it. And so just remember, one end of the bond is going to be taken up by the hydrogen and the other end will have the halogen. So you're going to end up with alkanes that have halogens on them, so organic halides. Last one, we have hydration, which is where you add water. We're actually going to look at this kind of a reaction in more detail when we start looking at polymerization. Well, I guess that's a different form of hydration, actually. Never mind, don't worry about that. So with this, you have your alkene and you're adding water. A hydrogen comes in. And so remember, with water, you're breaking it up into like H and OH. And so basically what happens is one hydrogen comes in and takes the place on one carbon, and the hydroxide comes in and takes the place on the other carbon, which leaves us with an alcohol. And for these types of reactions, always remember that there's two possibilities, because you could have the hydroxide on, one or the other carbon. So just remember to make a note of the fact that two isomers are possible there. Okay, the next type of reaction we're going to look at is elimination. So an elimination reaction happens when atoms from an organic molecule are removed, which probably seems pretty obvious because it's elimination, right? And so when atoms are removed, then a double bond can form between the two carbon atoms because they have those bond spots available now. So this is basically kind of the reverse of an addition reaction. And one of the uses for this is to make ethene, which is used to ripen fruits and manufacture plastics. Okay. That's weird. It should be ethane because polyethylene is basically like where you make a polymer out of all of these kind of like ethane groups. So I'm not totally sure why they have ethene there, but okay, so let's look at some of the possibilities here. There's three groups of organic molecules that can undergo elimination reactions if you have certain chemical and physical conditions. So with these types of reactions, you do need to know what conditions are required in order to make this reaction happen. I can tell you there is a question on reactions on the test, a written question, and if you are asked to identify any kind of reaction, you also need to identify any any conditions that are required for that reaction to proceed. So these are a little bit more specific than the addition reactions we just looked at. So the first kind we can look at is dehydration, where you have an alcohol and it basically, you lose the hydroxide and a hydrogen to form water. And then you end up with a double bond on the carbons where those two atoms were attached, or in this case, polyatomic ion. In order to do this reaction, though, you do need to put energy into it because you're breaking apart like more stable bonds, right? So it has to be heated, and this also happens in the presence of a strong acid catalyst, okay? So definitely things are required to help these happen. Dehalogenation is when you have an organic halide. So here we have like ethane basically with one halogen here. This happens in the presence of heat and a strong base. And so the base has this hydroxide component, which is going to be able to combine with the hydrogen from the one carbon to form water, and the other carbon is going to be able to release the halogen, again forming a double bond. Okay, so these are all just different types of elimination reactions, but they have special names because of what's happening specifically in them. The last one we'll look at here is dehydrogenation. And so just like the name implies, you're taking hydrogens out. So you start with an alkane, and very high temperature conditions are required again for this, because basically that means you are kicking off two hydrogens to form hydrogen gas, resulting in a double bond there. Okay, there's a little bit of information here about the term cracking, because we talked about it in the last section, but it technically has two meanings, because as we've seen, it's used to refer to the process of breaking large hydrocarbons into smaller hydrocarbons. So that's what we looked at when we were in the last lesson. But it can also be used to refer to the removal of hydrogen, which is kind of like referred to as cracking the hydrogen from the ethane. This isn't technically, so the first kind of cracking we looked at is technically the real cracking, but within industry, sometimes different types of terminology become adopted, even if they're not technically correct. And so this term for cracking is used to apply to dehydrogenation in industry. But we won't worry about that too much in Chem 30. For you, just think of cracking as breaking those larger molecules into smaller molecules. All right, we'll do some examples of elimination reactions in a minute, but first of all, we're just going to cover substitution as well, and then we'll go through some examples. So a substitution reaction is when a hydrogen atom or a functional group is replaced with a different functional group. So again, the name really kind of gives it away. You're substituting one thing for another. So with substitution, two compounds react to form two different compounds. So here you can see an example of substitution. We have methane, and we add in chlorine, and under certain conditions that's going to allow one of the chlorines to take the place of the hydrogen, and this other chlorine is going to attach to the hydrogen to form hydrogen chloride. So you can see how there's just a straight up substitution. One of these atoms comes in and switches out with one of these atoms from the other molecule. So you can think of this as being similar to the double replacement reaction that you would have learned in Science 10 and covered again in Chem 20. With addition, two compounds react to form one product. So basically the difference here is in this one, you just swapped out two atoms. In this one, you have a double bond that is going to open up to free up space for more things to come in. So with the addition reaction, the chlorine actually just gets added on and you end up with a single product. And then lastly, we have elimination reactions. And so with elimination reactions, you have one compound that reacts to form two products. So basically, usually you have those the conditions that we looked at, like heat or catalyst. And so basically what happens is you're removing parts from the original compound so that you can form a double bond. So in this case, it was a hydroxide and a hydrogen that get removed to form water, allowing these carbons to form a double bond. So remember, with the elimination reaction, you do need to have those like the energy and or a catalyst that's going to help this reaction proceed, because it's kind of moving energetically backwards. So alcohols and alkyl halides are compounds that commonly undergo substitution reactions. So alcohols react with an acid that has a halogen, and the halogen switches place. So that's kind of what we just looked at on the previous, or no, we just looked at a halogen on the previous slide, not an acid. So basically here you have your acid, and then you have your alcohol. The hydroxide is going to go and join up with the hydrogen to form water, and this bromine is going to jump onto that bond. So we see that there's just a switch, but you still have two reactants and two products, just like that double replacement reaction like I mentioned on the previous page. Alternatively, you could have organic halides react with a hydroxide ion. So this one we're looking at an acid. In this case, the hydroxide is coming from a strong base. And again, we're just going to see a switch out happening where the bromine is going to be released and the hydroxide is going to jump in, and we're going to see an alcohol being formed. Okay. So with the reactants for substitution, you're usually starting with an alcohol or an alkyl halide. Okay, so alkanes and aromatic hydrocarbons can also undergo substitution, but because they're really unreactive, the reactions need to be forced. So aromatics can react with chlorine or bromine in the presence of a catalyst, and the halogen switches place with a hydrogen. So basically you have your aromatic ring, and even though they don't represent it, we know that on these carbons there's one hydrogen each, right? And so basically one of those hydrogens gets replaced with a chlorine. So we end up having this halogen side group here. And then we have a hydrogen halide as a product because this hydrogen has joined on to the remaining halogen there. Let's see, I think that's everything. Oh, wait, did we go over this? Undergo substitution reactions. That's weird. I thought we went over this, but maybe not. So alkanes undergo substitution reactions when considerable amounts of energy, so it's usually UV light you'll see pretty often, and it'll be written above the arrow to show that it's just helping to facilitate the reaction happening. So basically, we have the presence of energy, which is going to help the alkane to replace hydrogens with halogens. And multiple products are going to be formed if you have an excess amount of halogens. There's lots of different possibilities, right? So in this case, we have 10 chlorine molecules to react with these 4 methane molecules, and lots of different reactions could happen. You could have one chlorine swap place with one hydrogen. You could have 2 chlorines swap with 2 hydrogens, 3 or 4, right? And then you're going to end up with 10 hydrogen chloride molecules. So if you do the math here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 chlorines, so that's half of these 10 molecules, and the other half, so the other 10 chlorines are bonded up with the hydrogens that it substituted out. All right, so here's a summary of the reactions, and this can be handy to kind of keep an eye on while you work through your problems, at least at the beginning, but do make sure that when you're getting ready to write the test, you are able to work through these kind of problems without this chart. So basically the chart just gives you the types of reactions we've looked at so far. How many reactants may or may not be super helpful, but this probably is quite helpful, is like what are the type of reactants, so if you can remember to look for these type of reactions, and then the type of products, and also the required conditions. Okay, so this is meant to be like a little bit of a study guide for you guys. There will be an updated one of this after we look at esterification in the next section. So let's look at doing some examples that are going to include all of the different types of reactions we've looked at now. And this is what you should be able to do, is identify any of those types without knowing for sure which kind it would be. So you won't always be told what kind of a reaction is happening. You need to be able to identify the reaction that's happening and predict the products. So in this one, we have an alkene and we have a chlorine molecule being added to it. So whenever we have an alkene or alkyne, remember that's an addition reaction. And basically what's going to happen is this chlorine is going to come in and replace either end of this double bond, right? So you can always flip back here if you need to. Types of reactants, you can see alkenes are right here in terms of addition, and we're going to end up with a single bond as a product, right? Because this is going to come in and replace those bonds. So now we're going to have, instead of CH2, we're going to have, we'll still have CH2, but one end of this double bond is replaced with a chlorine. and then bonded to the other carbon. Same thing for this carbon. It's going to have a chlorine attached where that double bond broke. It's going to have a hydrogen still attached, and then it's still going to have the bond to the CH3 at the end. So we end up with this single product. So naming the products, we would say that we have 1,2-dichloromethethpropane. So 1,2-dichloro propane. Okay. Next one here, we have CH3, CH2OH. So that means we're working with an alcohol here. And we have a hydrogenated halogen. And so what's going to happen here is we want our hydroxide is going to switch places with the halogen, and the hydroxide is going to link up with the hydrogen from that hydrogen chloride to form water. So HOH will be one product, which is water, and we're going to end up with CH3, CH2, and attached onto there will be the Cl. Okay, so CH2Cl. And so basically what we would have is chloromethane. Okay, because we just have the one chlorine, you don't have to give a number for it, because you would, if it was on this one, you would just number this carbon number 1, right? There's only one possibility there. Let's see, for this one, a little bit different. We're given the product, and we need to guess what the reactants could be. So in this case, we have alcohol as a product. And so with this type of reaction, there would be two possibilities, actually. So the first one would be that we have, and one of the ones that we probably think of first would be the halogenated hydrocarbon, and we're adding in water, which is going to, the OH from the water will substitute for the halogen. So for example, we would have this base molecule, but instead of a hydroxide there, we would have a chlorine. So we'd have like CH3, CH-Cl, and then dash CH2 and CH3. So in this case, and then you would add, so plus water, HOH. So in this case, the hydroxide would jump in and take the place of chlorine. And the only other thing is, in that case, you would be left with, actually, so it couldn't be substitution, because you would swap out this hydroxide, chlorine for the hydroxide. So as an additional product here, you would have HCl, right? They didn't show that, so that means actually the only other one would be, so this would have been substitution. So sometimes with these, you just have to try out what you can and then see if it works, and sometimes you'll catch things like that. So because they didn't say HCl, the only other option would be addition. And we could have also figured that out because we only have one product, and if you look at our little chart here, the only ones with one product are addition reactions. So in order for an addition reaction to result in this, we would have needed to have this start out as an alkene. So we would have had CH2 double bonded to CH bonded to CH2, CH3. Again, plus the water, HOH. And in this case, the hydrogen is going to take the place of one end of the bond, and the hydroxide will take the place of the other, and so then we would end up with this product. So in this case, to name our reactant, we would have methethprobutene, or but1ene, I guess. But1ene as our reactant, and then that would give us this as a product. Okay. Let's see. One more of this would be 2-bromo, 3-methylbutane, and water. are the products of an organic reaction. So we end up with a halogenated, an alkyl halide. So maybe let's draw that out. 2-bromo-3-methylbutane. So we're going to have bute would be 1, 2, 3, 4. And on the second one, we're going to have a bromine. And on the third one, we'll have a methyl group. Okay, so that would be, then this one would be CH3, C, 1, 2, 3, so this would be CH. This one would be 1, 2, 3, so it still has an H, and then the one on the end would be CH3. And we also have water. Okay, so we have HOH plus this are our products. So in that case, what kind of a reaction could have happened to make these products happen? So we would have had, in this case, the bromine here, when you're doing these types of reactions, especially if you're given a product, always think about, you're either looking for like a hydroxide group, a double or a triple bond, or a halogen. Those are usually the ones you're looking for. So in this case, we have a halogen here, and one of our other products is a small molecule. So what would have made the most sense to happen here is that this hydroxide was originally here and the bromine was originally here. So we would have swapped places there. So we need to make an alcohol for our reactant where the bromine is switched out for hydroxide. So we're going to have CH3-CH, and instead of the bromine, we'll have an OH down there, dash CH with that methyl group off of it, CH3, and then CH3 on the end. And it would have had to react with HBr. So naming these would be hydrogen bromide, and for this one we would have, let's see, carbon 2. So that's where our alcohol is. And carbon 3, 1, carbon 2, carbon 3. Yeah, so 2, let's do this one would be carbon 2. So first we have to name our side group. It's going to be 3-methyl. 1, 2, 3, 4, butane, and that was on carbon 2, so butan 2-all. Okay, so there's the names for our reactants. All right, that is actually everything for today in terms of examples. I am going to go through the practice problems though. If you don't need help with the practice problems, that's great. If you're going to do them and watch the video, please try them first because that is your best way to learn. And then if you finish those up, make sure that you work through these practice problems in the textbook before you go on. Like I said, there will be questions on this on the test, so you do want to make sure you've done these practice problems and you know how to work with these reactions pretty solidly. Like you definitely want to have them down and understand how they work. Okay, so next time we'll be looking at the last component of our organic reaction. So we'll be looking at esterification. So if you're wrapping up the video, I will see you in the next lesson. If you want to stick around, I will go through the solutions for the practice problems. So for practice problem number 1, we're stating the reaction type, drawing and naming the products for each reaction. So in this one we have an alkene and we have a small hydrogen halide. So basically what's going to happen here, this is going to take the place of one end and this is going to take the place of the other end of that double bond, and they're going to be removed. So basically we're going to have CH3 CH, oops, shoot. Let me just see if I can get rid of that. So CH3 and then CH, we're going to have a hydrogen come in and join there. So let's make that CH2. And then this one, we're going to have the CH and a chlorine is going to take the place. So CH and then with the Cl coming off of it, and then CH2, CH3. Okay. So that would be an addition reaction, and naming this just keep in mind there would be two isomers. So it's either going to be 1, 2, 3, 1, 2, 3. It's either going to be 3-chloropentane, or it's going to be 2-chloropentane, because the hydrogen could have gone on to this one and the chlorine could have gone on to that one. So just keep in mind there's two possibilities there. For the next one, we have a cyclic hydrocarbon with halogen off of it, and it's reacting with a strong base. And so that's going to be a substitution reaction where this hydroxide will take the place of the chlorine. So substitution, and we're going to end up with this cyclohexane with a hydroxide off of it. So that would be cyclohexanol, right? Because it's an alcohol and it's cyclohexane. So cyclohexanol, you don't have to give a number for the alcohol functional group because there's only one group there. And then as our product, we would have as well, the potassium is going to link up with that chlorine. So we're also going to have potassium chloride there. Okay. And that would be aqueous if you had to worry about that. 2-bromobutane. So with this one, we're going to have butane, means we're going to have 1, 2, 3, 4 carbons, and on the second one there's going to be a bromine, and all the rest of them are going to be like CH3, CH, CH2, CH3, just the standard kind of amounts of hydrogen. We're reacting it with a strong base. So again, that strong base is going to jump in and take the place of the halogen. So, oh, wait a minute. Nope, I'm not thinking about that right. The strong base with an alkane is not, this is just going to facilitate the reaction. So this is actually going to be an elimination reaction. And so this is where it's good to keep in mind your different rules and why it's good to look at this table. So if we look at heat and strong base, and we start with an organic halide, you can see that this would be our reaction elimination, and we're going to end up with an alkene plus the hydrogenated version of the halogen. So basically we're going to end up with, let's see, this will be replaced by a double bond, and so we could have CH, if this one is replaced, you could have a double bond here or here. So if the double bond is there, we're going to have CH2 double bond, CH bond, CH2, CH3. Or you could have CH3, CH double bond, CH bond, 1, 2, 3, CH3. Let me just make sure that's 3, 6, 8, 2, 4, 7, 8. Yeah, okay, so I kept those proper. So then it would just basically be but1-ene or but2-ene, okay, for your names. Next one we have here is we're reacting an alcohol with a strong acid. So basically that's going to be another elimination reaction where you're going to have the hydroxide being replaced, or like eliminated, I guess is the better word, to form a double bond between these two carbons. So if we draw this out kind of properly, it's kind of drawn out weird here. We would have had CH2, CH with the OH would have been coming off of that one, and then the CH3 here. So what we want to do is if this guy goes away, you could either have a double bond here or a double bond there. So you would either have, I'm not going to draw this one out just to save time, but you would either have, we would get rid of this double bond there, which would be 1, 2, 1, 2. So that would be but2-ene, or if the double bond had gone between these two, it would be but1-ene. Okay, so those are your two possibilities there. And then the other product of that is always going to be water, okay, because this hydroxide is going to leave and react with the hydrogen from the acid to form water. So you'll have but2-ene plus H2O or but1ene plus H2O. Let's see, 1-methylcyclopentene. Okay, so let's maybe sketch that out really quickly. Pentene, and it has one methyl group off of it. And then you're adding in hydrogen. So if we have an alkene, we add in hydrogen. It's basically, oh, sorry, I didn't, 1-methyl. So then you would have that. We had to put in our double bond. That is extremely messy looking, you guys. But let's see if I can make that look a little bit more like an actual structure. Okay, so there's our cyclopentene. We add in the double bond. And then we have a methyl group, and the methyl group has to be off of where the double bond starts because it's on the first carbon. Then we add in hydrogen, and basically what's going to happen is it's going to come and fill in those two ends of the double bond, so it becomes cyclopentane with that methyl group. So your product is going to be, let's see, no, you wouldn't even have to put in the 1 because there's no double bond in here. So it would just be methylcyclopentane, and it would be an addition reaction. Okay. For this one here, we have an alcohol, and we're adding in a hydrogenated halide. And so the alcohol is going to be replaced by this bromine, and the hydroxide group, the hydroxyl group from the alcohol, is going to combine with the hydrogen to form water. So it's going to be HOH, which is water. And we're also going to have this whole structure here with a bromine on top. So again, I won't waste the time drawing it out for you guys, but it would be meth-eth-prop-bute. So it would be 2-bromobutane. Okay, would be your product. All right, so the solutions are also listed there as well, if you guys need to have a look at that. But let's just bomb through these last couple of practice questions here really quickly. So the reaction of ethene and oxygen produces, so this one is a little bit tricky because we didn't cover it today. We have an alkene and oxygen. So ethene is going to be like this, right? Hydrogens. And we're adding oxygen, but we didn't talk about that today. What you need to recognize here is that this is combustion. You have a hydrocarbon plus oxygen always produce carbon dioxide and water. Okay, so that's that one you should still have memorized from Science 10 and Chem 20. The main problem that happens for Chem 30 students is they kind of forget all the simple basics, and they're trying to figure out if this would be like, how is oxygen going to substitute on here so that we can get rid of that double bond? So don't overthink things. Practice number 3, we have 2 moles of chlorine gas reacting with 1 mole of acetylene. So we have C2H2. So basically 1 hydrogen, 1 hydrogen. What does that leave for a bond between the carbons? A triple bond. So we have an alkyne, and then we have 2 chlorine molecules. So that means we have a total of 4 chlorines here. So that means we could break off one of these bonds and replace, so be hydrogen, hydrogen, chlorine, chlorine, whoops, chlorine. And then we can break the other bond by adding on the additional chlorine. So let's make that down to a single bond and add on 2 more chlorines. And so we're going to have CHCl2, CHCl2. So B, answer B there. Okay. For this one, aqueous bromine is added to hexane and hex-1-ene in the presence of light. What's going to happen to the hexane? Hexane is going to go substitution, right? So it's going to have the bromine is going to substitute one of the hydrogens. Hex-1-ene is going to undergo an addition reaction, right? So the double bond is going to break and the bromine is going to get added into there. So we're going to have, what did I say for the first one? Substitution and addition. So D would be the correct answer there for number 4. All right. That's the same one. Practice number 5. So in this case, these reactants undergo what kind of a reaction? So C2H4 is an alkene, and if we add in bromine, it's going to be an addition reaction. So it's going to get rid of that double bond, and we're going to end up forming the product of the reaction will be 1,2-dibromo. We've broken that double bond, so it's going to be an ethane. Okay, so that would be C for that one. Practice number 6, we've got propan-2-ol can be produced from propene and water, as represented by this equation. The production of propan-2-ol from propene is what? Well, we're removing that double bond and we're adding in the OH, so that is an addition reaction. And propan-2-ol is likely to be soluble or insoluble in water. Well, it's a short chain alcohol, so with that hydrogen bonding there, it should be soluble because it should be polar. Practice number 7, we have a couple of reactions. The reaction represented by equation 1. So again, we have ethene plus a halogen, and we end up with C2H4Cl2. So what's happening there is we're breaking a double bond, so that's going to be an addition reaction. And what do we end up with for a product? It's going to be an alkyl halide. So you're breaking that double bond. You're not going to have an alkene anymore, so it would be B for that one. Practice 8, pretty simple. So we're reacting ethene gas and chlorine. So again, double bond is going to be broken. We're going to substitute in the chlorine. So that's going to be an addition reaction, which might have been confusing because I just said substitute, but it's going to be an addition reaction, and you're going to end up with an alkane that has those chlorines on it, so that will be A. Practice number 9, bromine added to propene. So again, you would have an alkane in the end, and because that's just addition, sorry, not substitution, that should be your only product, is the 1,2-dibromopropane. Practice 10, during a substitution reaction, there could be a break in a carbon hydrogen, right? That's when you substitute out that hydrogen that's on a carbon for like an alcohol group or a halogen or something like that. Okay, so that's everything for reactions. Please do try all of those practice questions because you need to know how to do that for your tests, and I will see you in our next lesson on esterification.